common mode issue, that the gain biasing, the output biasing issue. So here also, if you do the same thing, VCM, and you see, you can see what is happening to the output node, and then you can plot this simple curve, what is happening to the V out, because both are same. They are ultimately a common mode operation, and this V in CM. So V in CM and VO CM. So there, whatever curve we have discussed, you can plot and try to see what is the curve coming, how steep it is, etc. You can look at that. That will give you a good idea that okay, if you want to adjust the V in CM to find out the orbitally established output DC bias point, it will be difficult. So these two things you can do, and then uh, uh, please complete the reading of the differential amplifier stage. And tomorrow we will look into the other configuration, which is this differential amplifier with current mirror load, and that will also help us in going to the uh, stage where we have operational amplifiers design. Even with today's class, I can cover a very nice operation amplifier topology after covering the differential amplifier. If you allow me some more time, maybe I can, even with today's background, we can cover a couple of op-amp design, nice op-amp design. But this one will help us in covering some of the standard topologies also. Where is the just yes. So I can very quickly, maybe just because we have covered some of these differential amplifiers. Anyway, let us do it tomorrow. So the op-amp based on the differential amplifiers, how do we design op-amps, that we can cover maybe tomorrow. Quickly, just one. Ultimately, for op-amp, what we have is it's a two-stage amplifier. First stage is differential. Second stage can be single-ended or differential. So based on the topology that we have studied, one possibility is this. Can anybody tell me what is the gain of this circuit? What is the gain of this circuit? Anybody can tell me? How will you calculate the gain? If I, this is the differential amplifier. Only thing is I have added another stage. This is a common source stage. This is like a common source stage. So this first one is the differential amplifier. Second stage is a common source stage. So anybody can tell me how will I approach the gain calculation in this stage? Based on the circuit concept that you have studied so far, single-ended differential, can we arrive at the gain expression for this stage? V out is here. Yes. Yes. Are
So if there
you?
is proper DC biasing, then can we just multiply the gain of two stages?
Yeah. So what is the gain of the two stages? So can we look at the gain? So look at the signals, how the signals are flowing. So uh, whatever input you provide, suppose you have, uh, you know, VD, V in plus, V in minus. Suppose I decompose it into VD by 2 plus minus. So suppose this is plus VD by 2, this is minus VD by 2, whatever. So differential signal VD and VD by 2 minus VD by 2. So for VD by 2, I get GM VD by 2 here, GM VD by 2 here, and same minus GM VD by 2 over here. So now, if you look at this, what is this forming? Like if I call this M3 and 4 and 5 and 6. So what is M3 and M5 forming? M3, M5, what is it? Quickly.
Current mirror.
Current mirror, right? So there's a direct connected transistor M3 and then M5 is output transistors. It's just like a current mirror. So what happens then? Whatever GM VD by 2 flows here, GM VD by 2 same current basically appears here. Then what happens here? Again, the same current enters into this direct connected MOSFET, the same small signal current GMVD by 2, right? So now what is this transistor forming? If I call it M7, M8, they're also forming current mirror, right? So whatever is current in M7 is a direct connected MOSFET, and M8 is forming a current mirror with that. Therefore, the same small signal current will get reflected here also GMVD by 2. Is that clear? Whatever GMVD by 2 came in this input transistor M1, same went in M3, it got mirrored in M5, it came in M7, M7 to M8 again it got mirrored, and it came GMVD by 2 over here. Is that clear?
Yes, sir.
Yes, sir.
Likewise, on the other side, minus GMVD by 2, it will come here and will get mirrored into this, minus GMVD by 2. Right. So here, if you look at the overall output, what is the impedance, net impedance at this stage? What is the net impedance? So here, ultimately, what is happening? So the upper MOSFET is providing minus GMVD by 2, or lower MOSFET is providing, GMVD by 2. So if you look at the overall small signal current, minus GMVD by 2 coming here, and GMVD by 2 coming here. So if I look at the output impedance, what is it? RO up parallel RO down, it is simply RO by 2, right? RO6 parallel RO8. And then you have the small signal reverse the direction, it is basically same. So basically, if you look at, if you reverse the sign, it will be plus GMVD by 2 in the direction. Therefore, the net current going out of this resistor is simply sum of these two. Therefore, the output gain will be RO by 2 given by RO parallel R6 times GMVD by 2. And now this GMVD by 2, if you take plus minus, anyway, it gets summed up. So you get just GMVD. So this is the GM RO by 2 gain you are getting. Now, why we have done this? So it will become more clear maybe when I try to, this is clear, right? So how the overall small signal gain I define, starting from the input signal GMVD by 2, coming to the output stage, finding out the small signal current flowing into this transistor, and then looking at the current going into output small signal resistance. So that gives us the voltage, overall small signal voltage. So once I know the small signal current provided by the upper and the lower MOSFET, I know the small signal resistance between the output and the ground provided by these two MOSFET. Therefore, this way you can calculate the output signal. This is clear to all of you, this thing, how did it come?
Yes.
Yes, sir.
Now, what is the difference? Why have we included this particular topology? And here also we have a output node, which is basically having a high impedance stage, which is not a well-defined, basically, it is not a well-defined DC point. So we will see that. So let us, here, if I modify certain things, suppose I keep it input stage same, if I add some more transistors in stack. Now, suppose I do this, right? So these are additional PMOS, and one NMOS transistor, just like in the cascode amplifier, right? So I have just added two more transistors in cascode. Now, what is the situation? What is the, how do I find out the gain? You can figure out, right? So this signal, the M6 and M8, you know what is the small signal current provided. It is remaining same. Till this point, it is remaining same. Till M6 and M8. Only thing is now you have this cascode two transistors coming into picture. And then in order to find out the output signal, I need to find out what is the small signal current flowing again to the output in presence of this cascode devices. So what will be the value? So approximately, what is the order of the small signal resistance at the output now? That is GM RO square, right? That you know, this is the cascode stage, right? And now we are getting the small signal current, which is proportional to GM right? So definitely, again, just like earlier case, we are getting GM RO square factor. So the gain factor in this case again is going to be GM RO square. At least that much we can appreciate. Is that clear?
Yes, sir.
Yes, sir.
So here we are seeing that the input is differential, but the output is single-ended, and it is a very high gain stage. So overall gain will be dominated by the second stage. First stage, the signal gain is not much because it is direct connected, but the output you are having a large basically gain. So in this case, it is like, of course, the output impedance is still too high. We don't have a good output impedance. It is still too high. So uh, this kind of circuit is called operational transconductance amplifier. In order to make it an op-amp, you need to also make the output impedance low by adding a buffer stage or a common drain stage. We will discuss that later. But at least you can understand that in this case, it is just like whatever operational amplifier you have studied with differential input and very large gain. This kind of operation it will carry out. Only issue right now is the output impedance, which is still high. And the DC point is also not well established. For that, also we need to have some strategy. So if you use it as a unity gain amplifier like this, for negative feedback, unity gain amplifier, then output and input DC points are the same. Whatever output DC, whatever input DC point you apply, it will settle the output DC point also. So likewise for differential operation, if you any other configuration also, we can establish the right kind of DC point. We will study some of the techniques maybe tomorrow. So just because we have already covered these topologies, so you can see that for understanding the gain, etc., we will not do all the analysis again and calculations and derivations again. Based on whatever we have discussed, in many cases we may be able to just find out or intuitively arrive at the expression of the gain. So this is one example of operational transconductance amplifier or OTA that people use, and we will look into several other topologies depending upon depending upon certain applications. Some topologies may be applicable. Depending on some other applications, some other topologies may be applicable. So we'll look into all that. Okay, so any question before let us already have taken a lot of time. So any question before we conclude? Yeah, so fine. So let us then meet tomorrow. And first of all, I will make sure that tomorrow I come with a better planning, because extempore many times it is getting messy. So I have to at least plan what I have exactly what exact flow is going to be there, etc. So that I will do, and also I will have to speed up a little bit. So uh, please take the reading seriously because of lack of time, and especially because I have to speed up. I may not be able to teach everything. Some parts which are already there easily in the book or in some video lectures, I may give you to read or go through. That will only help you in coming to a level where you can get started with some nice projects. So if you are really serious about getting into some project activities, please take all these reading, etc. Seriously, and also the assignments, of course, whatever we are doing. So tomorrow I will let you know. Maybe we will have some time for the simulation exercise also. Whatever doubt is there in the last assignment, we'll do that. And this part also, theory part also, we will carry out. Okay, so let us conclude today.
Thank you, sir.